All right, thanks everybody for coming. My name is Kevin Tubbs. I'm the field CTO for HPC and AI at WEKA. Happy to be here in the booth with LapLup to talk about accelerating HPC and AI workloads with WEKA NeuralMesh. So one of the things we're here to talk about, and one of the things we notice, AI is evolving fast. Over the last 2-3 years, we've seen a great growth from training all the way out to agentic workflows. So when we were working on training, a lot of the things were about high throughput, training multi-models, foundational models. Then we started moving into LLMs. We got a large adoption of generative AI. And then after that, we moved into reasoning and now into agentic workflows. And as we get this transition out into the different ways that it involves to use AI, you're getting a large change in the volumes and amount of data. And the key thing is we're learning that the data infrastructure needs to keep up. So one of the key things about that is real-time responsiveness. So I'll talk a little bit more about WEKA and how we do real low latency file systems. The other key thing we have to watch for is explosive amount of data growth. The more we use AI, the more we change the algorithms, the more data that it uses and drives, so the explosive growth of data. And then the last key part that's important is unpredictable workloads. The AI infrastructure that you designed 2 years ago to what you designed 12 months ago is changing. So you want to design an AI infrastructure to be able to optimize what's there and be able to handle workloads as they change and evolve. And we'll talk about that and how we're able to do that at WEKA. So the key thing there is we needed a new approach where a software-defined microservices approach allows us to be deployed on-prem, in the cloud, integrated into a lot of different software stacks. And being the microservices infrastructure, we can integrate all the way up into the frameworks and things like that. Also things like backend.ai. So we want performance that scales, flexibility without trade-offs. And that's that flexibility of multiple platforms, multiple clouds, multiple backends, different types of hardware. And then from that, you want to get efficiency that compounds. So why NeuralMesh by WEKA? So NeuralMesh is the world's only storage system purpose-built for accelerating AI and modern workloads. When we, the founders were able to design it, we saw a change in inflection in technologies with NVMEs and high networks, but a lot of the software and storage systems weren't designed for that. So we designed it from the ground up to be able to take advantage of whatever network's there, whatever NVMe's there, and optimally deliver a data fabric for all workloads. So one of the key things there is efficient multi-tenancy. You want to be able to have extreme performance. And I'll give some examples later of production environments where you can see large performance. But the key differentiator there that we have to have is ultra low latency. I want to be able to deliver a sub-microsecond for my storage. And I'll even give some examples of being able to deliver that sub-microsecond on inferencing workloads allows us to do some things that are approaching the memory wall. Other key things are security, so we have a lot of sovereign AI use cases. And then our last main ability is what happens at scale. So a lot with GPU workloads, training and inferencing, what happens when you scale to thousands of GPUs? You have the same thing with storage. So we want to make sure from our perspective, we scale out to exabyte and beyond, and we're at the point that we have quite a few customers that are on the exabyte scale. So how we do it at WEKA, so our NeuralMesh product, like I said, is software defined. We actually can deploy it in 2 ways. We have a dedicated, NeuralMesh dedicated, and that's where we can work on any OEM hardware. It has NVMEs and the right type of network, and we balance that design. But that same software, I can employ it on different shapes in the cloud. So I can employ it in AWS, I can employ it in GCP, OCI, and a but from there, I just need to be able to take advantage of those GPUs and those NVMEs and turn them into a file system. Another approach we have on the right is NeuralMesh Axon. When I'm able to do that is if I have a cloud environment or environment that I want to actually recapture and take control of stranded NVMEs on the GPU server, I can actually deploy NeuralMesh on the compute servers themselves and create a file system out of that. We have some use cases there in the cloud that because I have a sunken cost that I'm using those GPU servers, I get added performance and utilization just by running the software on top of the same infrastructure that I'm using. So what do we get from that? We use NeuralMesh for stream performance for AI workloads, kind of 4 key areas. Also kind of show you the evolution. Like I said, we started with training. We reduced training model times by 90%. By making sure that we can increase high throughput to the data, but also delivering it at high IOPS. Also checkpointing, we can speed that up to make sure that you have efficient and scalable training. We've also been able to accelerate the performance of the storage by 5x, and that's mostly by designing our stuff to be POSIX. So you're going to be able to use POSIX, full client, low latency access, of course, to NFS and other protocols. In doing that, we've also been able to expand research. So by getting training done faster, getting more access to the data, we've expanded research capacity for certain customers by 6x. And then towards the end, it gets to our inferencing use case for a product I'll talk about later, where I'm speeding up time to first token by up to 41%. And I'll go into more details later on that example. So, earlier we talked about data infrastructure needs to keep up. This is a production environment of one of our customers that are large scale training. They have over 100,000 GPUs and they've scaled to that over time. And they've been running production scale for years. So what you see on the screen is actually a throughput or modeling observability of our platform over a month. And here you can see the throughput is 6.85 terabytes per second. So this is an ability to do sustained throughput, but you also look at it, we're also delivering 87.1 million IOPS. And the key thing here is I'm able to deliver high throughput, but because I'm checkpointing, because I'm going through multiple stages of training, there's actually small IOs that are going on, and that's why we have the high IOPS. But our platform is designed to be able to deliver all of that mixed workload, various workloads on the same software-defined platform. So why WEKA for HPC and AI workloads? Higher AI ML performance, ability to deliver the same performance for the HPC or simulation side, the same performance for the ingestion of data, data analytics, prep, all the way to training and out to inference. So there's no tuning when you're changing when you go from one workload to the other. We're multi-protocol in a single namespace, so you can read data into S3, read data into NFS, and then have immediate access to it on the GPUs from POSIX. So we're actually able to continue to workflow there. From there, we get better TCO both on-premise and in the cloud by increasing GPU utilization and using our agentic direction coding. Now I'm going to talk about some business outcomes. Like I said earlier, we have a large autonomous vehicle manufacturer. They were able to increase their productivity, but they moved from an all-flash solution. Like we talked about, flash has been around, but if I'm running NFS or NAS solution on flash, that's not the optimal way to do it. So they moved from that to WEKA, and they reduced their training workload from 80 hours down to 4. So this is a significant change and increases the productivity of the research team. We also have another customer, Genomics England. This is a life science HPC use case, but here's another case where you have cryo-EM microscopes writing data in, doing genomics analysis on it, doing HPC simulation, molecular dynamics type of simulations, but all of this all going on the same system. We were able to speed up the genome pipeline by 72x and 75 reduction in storage costs per genome by delivering a effective mix of flash and object storage. And then the last example we have is actually not an HPC use case, but the Sphere in Las Vegas. We actually drive the display on the inside and outside. So that takes a very large amount of I/O to drive traffic to that many pixels. But the other interesting part of that use case is from a creative perspective, it used to take those engineers that were designing and creating the visual scapes for the concerts and everything 6 months to design a full set. We were able to get that down from 6 months to 6 weeks, so that from a creative cycle, I have a lot more time to be more creative, creating more scenes, so they get a lot more productivity. I have some other examples. This is another use case for us in manufacturing. So high performance data platforms on GPUs. They had a Hadoop use case where they're getting data from different sensors, but they actually got to the point that they couldn't do the number of queries fast enough in a real-time perspective. And when they sized out the compute needs that they had, they needed hundreds of thousands of CPU nodes. But if they moved to a GPU accelerated database like Scream, they were actually getting more efficient compute. And with, on the order of 10 nodes, replace 100,000 CPU nodes. But in doing that, they needed to make sure they can feed the GPUs and run on top of a platform. So we were able to use WEKA combined with Scream to give a high density compute for data ingest at the edge, also integrated with Kubernetes, which makes it very flexible. So the top 3 use cases for WEKA: data lake, data lakehouse, being able to provide performance and also capacity, AI and ML analytics, and like I showed and talked about other HPC genomics, high performance data and media. We're able to solve all these use cases. So last, I'm going to talk about WEKA Augmented Memory Grid, or AMG. In the same way, we're able to do that in 2 different modes, dedicated or converged. In this case, we're creating a access to an integration into the inferencing stack. So we're working with VLLM and other inference routers. We've also open sourced this back into the community with LM Cache. We also work with NVIDIA's Dynamo platform and Nixel libraries. So we've integrated that. But this is what the stack looks like. We're able to integrate there, and I'll kind of show you what that does for the inferencing side. And this is on KV cache use cases, which is when I need to be able to save multiple conversations and turns. And if I can save it, I don't have to recompute it. And by doing that, I can reduce the time to first token. So if you see on the left, lower is better. So the gray is basically when someone asks a question to an LLM, they're going to have to do the pre-compute. If they ask the same question, same information, I'm going to have to recompute again, especially if it's multi-turn, they ask me another question. So the gray is every time I have to recompute. But if I save that KV cache to memory or to storage, I can retrieve it much faster than recomputing. So what you see on the orange is when I'm saving it to local DRAM. And what you see in the purple is when I save it to WEKA, which is petabyte scale, I'm actually able to recall on the same order. DRAM is still faster, but I'm able to do this on the same order. But it also helps when I scale out to multiple use cases, which we'll see in the middle. So now I have an inference router with multiple servers. If I keep running that on the same server, I create a hotspot, and I'll have to keep pushing that data out, which means I have to compute more. Having a augmented memory grid or a petabyte scale KV cache, I can now save it there, move it from server to server, and not have any hotspots. So it also helps with operational efficiency. And then what do we get at the end of the day for that? A high overall token throughput. So not only am I reducing the time to first token, that also improves the overall output of the tokens. And this is going to scale better when you use large context windows. And we're knowing one of the things we see in the models, the context window is growing and growing, and that allows you to bring more data into the LLM. So we're able to do that. As you do that, it's going to push more pressure on the KV cache. And the more you can use the KV cache, the more efficient your inferencing will be. So that's my presentation. Happy with the partnership here with LabLub. We're excited to do some work on how we can put our things into and leverage for backend .ai. So if anybody has any questions, I'd love to answer them.